so 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 in this problem, we're asked to find what is the principal stresses and principal directions for the given state of stress. So our stress element in this case has both normal and shear stresses. All right, we have a 3 kpsi along the x direction. We have a 9 kpsi stress along the y direction, and then we have a shear stress of negative 4 kpsi, which is why we're drawing the shear stress towards the bottom right corner of our stress element. All right, so in order to find the principal stresses, what we can do is we can find the determinant of our stress of the difference between our stress element minus sigma p times the identity matrix. All right, if we do that, what we end up getting is we get 3 kpsi minus 4 kpsi minus 4 kpsi and 9 kpsi from our state of stress, and then we would subtract our identity matrix times sigma p. All right, and we take the determinant of that whole thing. So what we end up getting is we have the determinant of 3 minus sigma p minus 4 minus 4 and 9 minus sigma p. All right, to take the determinant of a 2 by 2 matrix, it's really simple. We just take the products of the diagonals. So what we end up getting is we get 3 minus sigma p times 9 minus sigma p times minus the product of the other two diagonals. All right, so if we do all that, we end up getting what do we end up getting here? We get sigma p squared minus 12 sigma p plus 27 minus 16, and we can set that equal to 0. All right. Sorry, there should be a 0 over here. All right. So if we rearrange this equation and simplify it down, we end up getting 0 is equal to sigma p squared minus 12 sigma p plus 11. We can factor this out into sigma p minus 11 plus, times sigma p minus 1. All right, there would give us two roots for our equation. We get two answers for sigma p. Sigma p would be equal to 11 kpsi, and it would be equal to 1 kpsi. Okay, so for these two roots of our equation of our determinant, they are our equation. These are our principal stresses. We will rank our principal stresses as like a first and second principal stresses in 2 dimensions. So our first principal stress is greater than our second principal stress. So in this case, sigma p1 would be equal to 11 kpsi, and sigma p2 would be equal to 1 kpsi. Okay. All right. So going back to the problem statement, we are asked to find what are the values of our principal stresses. We did that. So now we're going to go ahead and find our principal directions. Okay. So to find our principal directions, what we need to do is we need to use the following equation, which states that our original state of stress minus our one of the values of our principal stresses times the identity matrix times our eigenvector, which is a 2 by 1 matrix. So it'll have two parts in it. We'll have it as v11 and v21, and that must be equal to 0. Okay, so we can evaluate this matrix really quick. If we plug everything in here, what we end up getting is we end up getting 3 minus 4 and 9 minus 11 times 1, 0, 0, 1. And then if we keep going, what we end up getting is we end up getting, and this becomes minus 8, minus 4, and minus 2 times v11 and v21. That's going to be equal to 0. All right, if we multiply this matrix out, we end up getting two algebraic equations. We get minus 8 v11 minus 4 v21 is equal to 0, and we get minus 4 v11 minus 2 v21 is equal to 0. As you can see, these two equations are actually essentially the same equation, just the second equation is the first equation divided by 2. So from either of these equations, you can get that v21 is going to be equal to minus 2 v11. Okay, so what we're going to do to determine our eigenvector is we're going to make an assumption. So we're going to assume that v11 is equal to 1. Okay, then if we assume that, we can say therefore v21 would have to be equal to minus 2 times 1, or it have to be equal to minus 2. All right, and then what we can do is that we're interested in we know that the eigenvector, right? An eigenvector has to have a magnitude of 1. Okay, so what we can do is if we take our vector v1 and we divide it by its magnitude, all right, we'll end up getting our eigenvector. Okay, so we can just take our value, so we put v1 in matrix v11 and v21 in the matrix form here, and we divide both of these by the magnitude of the both components. So we're just going to take v11, we're going to square it, plus v22, and we're going to square that, or v21, and we're going to square it. Okay, so what we end up getting is our eigenvector to be 1 over radical 5 and minus 2 over radical 5. Okay, so we're going to repeat the same process, but instead of using, so this is our first eigenvector v1, all right, and then what we're going to be looking for next is our second eigenvector v2. Okay, so we have 1 out of the 2 principal directions. Okay, so we got 1 is done, we're looking for number 2. All right, so we already have solved it for sigma p1. We're going to go ahead and solve it for sigma p2. All right, this would be a great time for you to stop the video and try to solve for sigma p2 if you want to. If not, you can continue to watch, but please try it out. What do you have to lose? Might as well see if you can get it correct. Okay. All right. So sigma p2, we said that was equal to 1 kpsi. So we can plug it into our equation here. So we have our original state of stress here, and we're going to subtract our secondary stress, times the identity matrix. So this is our second principal stress, was 1. All right, and we're going to multiply that by our second eigenvector here. All right. All right, so if you evaluate this out, what we end up getting is 2 minus 4 and 8 times v12 and v22, and we set that equal to 0. All right, if we multiply these both out, we'll get two algebraic equations. We'll get 2 v12 minus 4 v22 is equal to 0, and we'll get minus 4 v12 plus 8 v22 is equal to 0. From either of these equations, if we rearrange them, we'll get v12 is equal to 2 v22. So we can then set v22 equal to 1, and we can then, therefore, we can set v12 would be equal to 2. All right, and again, we want to create a unit vector for our eigenvectors. So if we do that, what we end up getting is we'll get we'll say that v2, the eigenvector v2 would be equal to vector v2 divided by its magnitude. Okay. So if we do that, our vector v2 is equal to 2 and 1. So 2 in the first row, 1 on the second row. And then the magnitude of this would again be 2 squared plus 1 squared, which again would be radical 5. So our eigenvector v hat 2 would be equal to 2 divided by radical 5 and 1 divided by radical 5. All right. So what we end up getting from all of this, all right, is you're like, okay, what the heck did these eigenvectors actually mean? Is that our eigenvector, our overall eigenvector matrix V is going to be equal to v1, the eigenvector v1 plus and the eigenvector v2. All right, so this is a 4x4 matrix. All right, and so just summing up the values, inserting the values we had from above. All right. Right. All right, and what these are equal to physically in terms of our original stress rate is this tells us the angle that the matrix had to rotate in order to get to our principal stress. So we will have the angle cosine theta p1, right, is going to be equal to v11. All right, the cosine theta p2 is going to be equal to v21. Sine of theta p2 is going to be equal to v21, and then cosine or sine of theta p2 is going to be equal to v22. Okay. So you could use this relationship here to solve for the angles, and you can then, and in the next video we'll show you how you can rotate the stress element from its original position to the position where the principal stresses are acting. All right. So to summarize what we did in this video really quickly is we were given an initial state of stress. To find the principal stresses or the eigenvalues, we took the determinant of the stress matrix minus the principal stress variable sigma p times the identity matrix. Once we did that, we ended up with a quadratic equation, which we could solve for the roots of the quadratic equation as being an 11 and 1. Using those roots, we could plug them back in to this relationship here. To find our first eigenvector, so if we plugged in sigma p1, we could find our first eigenvector v1, and then we could use the second one below. Eventually, eventually we can get to solve for our second one, v2. All right, and then once we had that all set up, we can find our two eigenvectors. We had our two eigenvectors, and we could relate those eigenvectors to our angles theta p1 and theta p2. And sorry, I just realized a typo. This should be sine of theta P1, not sine of theta P2.